Okay, welcome to Maths 101. The topic is quadratic equation and remainder theorems. Okay, so the various topics under this chapter, chapter 4, we have quadratic equations and their roots, quadratic inequalities and their solutions, and remainder theorem. We'll start with definitions, all the things you need to know in order to cover this entire chapter, and thereafter we consider several examples. Okay, first we have what we call the quadratic equation. So any equation of this form is called a quadratic equation with a not equal to 0, b and c are constants. They're called quadratic equations. Okay, now if you want solutions to quadratic equations, we have a number p is said to be a solution of a quadratic equation. Okay, if by replacing x by p on the left hand side and the right hand side, the quadratic equations are equal, so you get a solution for that quadratic equation. If at the end of the day you place whatever value you put p here, you get the same answer on your left hand and right hand side, then we say the value p is the solution. Okay, so when we have p1 and p2 as two distinct roots of a quadratic equation, say this, we have, it means it can be written, it means that this equation, quadratic equation, can be expressed in this form. So if you have two distinct roots, p1 and p2, as quadratic solutions to this quadratic equation, that means the quadratic equation can be expressed as this. Note the minus p1 minus p2. Okay, the general solution to a quadratic equation is always given, of this form, is always given as this. I know you call it the almighty formula, so that's the general solution to it. The next thing you need to know is about the discriminant. The discriminant is very important because it helps us explain the nature of any given quadratic equation you have. Now you know what a quadratic equation is. An equation of the form ax squared plus bx plus c equal to 0, right? You know what a solution to a quadratic equation is. You know that if you have two distinct equations, it means the quadratic equation can be represented in this form with putting in the distinct solutions. You know what the general solution of a quadratic equation is? It is this. Now, like I said, if you want to know the nature of any given quadratic equation, we use what we call its discriminant. Okay, now the discriminant is simply given any quadratic equation of this form, the quantity d, which is equal to b raised to power 2 minus 4ac, is called the discriminant of the equation. This is used to determine the nature of the root of the quadratic equation. So this discriminant b squared minus 4ac, very, very key. Okay, now if b squared minus 4ac is equal to 0, it means that that quadratic equation has equal roots. Okay, once you have equal roots or a perfect square, it means that the discriminant is equal to 0. Okay, and that means that this a squared quadratic equation a squared plus bx plus c has equal roots. If the discriminant is greater than 0, it means that the quadratic equation has two real distinct roots. Note, greater than 0. If the discriminant is less than 0, it means that that quadratic equation has complex roots. Okay, so these are three important things you need to know about the discriminant. One, that if it is equal to 0, it means it has equal roots. If it is greater than 0, it means it has two real roots. If it is less than 0, it means that it has complex roots. Okay, the next thing you need to know is that if we happen to have two roots, say alpha and beta, these are just notations. It could be a, b, capital A and capital B, okay? And they're roots of this quadratic equation. It means that the equation, you know, what we said, if they had distinct roots, it means that you can express the quadratic equation as x minus alpha into x minus beta. If you remember when we had p1, p2, we said it was x minus p1 into x minus p2. Okay, so if you happen to have roots alpha and beta of the given quadratic equation, it means it will satisfy the equation as you can see on the screen. Okay, now meaning that if I open this bracket, if you expand this bracket, that is x minus alpha into x minus beta. You try it on your own. You should get this here. If you expand, you should get this relationship. So if it turns out that this is the same as, remember that we said this was the quadratic equation ax squared plus bx plus c is the same with this, right? So if you open the bracket, expanding this two brackets, you should get what you see on the screen. And if you relate them to the quadratic equation, this equation and this equation, these two, they're the same, remember? I simply divided both sides by all the terms by a all through 0 by a2, and you get this term here, this quadratic. This is the same thing. Okay, if you compare the two of them, you can see that x squared is x squared here, and this minus alpha plus beta x is b over ax here, and alpha beta is c over a, right? So that's just what we've done, so that at the end of the day you can relate the two of them, because it means that this alpha plus beta is going to be the negative of b over a. That's how we got this, alpha plus beta, and the product alpha times beta is going to be c over a. You need to know this correspondence relationship by heart, that once you have these two roots, the formula will satisfy, basically saying that you can write it as, the equation can be written as x squared minus the sum of the roots times x plus the product of the roots equal to 0. And the sum of the roots is always minus b over a, and the product of the roots is always c over a. So you need to know that, okay? So, symmetry of roots, what do we mean by that? An expression involving the roots alpha and beta of a quadratic equation is said to be symmetric if alpha is substituted for beta and beta for alpha. The expression remains the same. So once the expression remains the same, when you substitute, interchange the values, then we say we have symmetry of roots. Okay, I need you to know these expansions you can see on the screen by heart. This ones, this you can get on your own, but just note them, that if you have alpha for beta all squared, binomial expansion, right, you have something like this, and that alpha squared plus beta squared can be written as this, and if you have alpha plus beta all cubed, it's the same as this, and it's the same as this. Okay, you will see the significance of this later, so this you need to know by heart. I will use it later during the examples. Okay, so any inequality relationship that involves a quadratic function is called a quadratic inequality. Okay, it's called a quadratic inequality. So if you have an inequality relationship and it involves a quadratic function, what's a quadratic function? Is any function that satisfies this or this. They're all the same thing, right? And that's what you need to know as foundation for status on quadratic equations. We've talked about discriminants of roots, right? We had said when you have them to be the discriminant, if you have the discriminant equal to 0, you have what? Equal roots. If it's greater than 0, you have two real roots. If it's less than 0, you have complex roots. Okay, so we are just getting foundations. Now the next thing you need to know is what we call the remainder theorem. So what do we mean by the remainder theorem? It simply says if px is a polynomial, okay, in x, then the remainder px is divided by x minus b is px. Then the remainder when px is divided by x minus b is pb. So you have a polynomial px. Now if you divide px by x minus b, the remainder will be equal to, so they're saying it implies that the remainder must be pb. Note, there's p minus b dividing the polynomial px. Okay, so if you divide px by the polynomial px by x minus b, then the remainder is always pb. Basically plug in the value b for x. Okay, so that's what we call the remainder theorem. So that tells you what the remainder is when you divide by x minus b. That must be pb. And then the next is what we call the factor theorem. So the remainder theorem states that The factor theorem is next. Factor theorem says that px vanishes, meaning that px goes to 0 when x is equal to a. So if px goes to 0 when x equals to a, then x minus a must be a factor of the polynomial px. Again, it's there on the screen. Let's read it as it is there. It's saying that if your polynomial px, when you plug in, wherever you put a in it, goes to 0, then x minus a is a factor of the polynomial px. Okay, so these theorems are very important. You will see us use them later. Okay, so we've learned a recap. We've learned a few things on. First, we started with quadratic equations. Okay, and we saw that if you have a quadratic equation, you have roots, it will satisfy the product of this form, right? And then we looked at the discriminant. Oh yeah, we even saw the general equation for it. We saw the property of the discriminant, which tells us the nature of the roots. Okay, we then looked at if you happen to have alpha, beta as roots of a quadratic equation, and then we saw that the two can be related in this form, right? Such that the sum alpha plus beta will be minus b over a, and alpha beta will be c over a. And that another way of writing this same quadratic equation is simply saying x minus the sum of the root times x plus the product of x of the root, equal to 0. And I told you to note this particular one. You can pause the video and write this out because you will need it later. You need to know it by heart. Okay, so we also considered remainder theorem and the factor theorem. The remainder theorem basically saying that if you divide the polynomial by x minus b, then the remainder must be pb. The other one says if you plug in the value, if you happen to have a factor x minus a, and you plug in the value a, and this vanishes, then if you plug, whenever you get x equal to a, the polynomial x equal to a, and it makes the polynomial go to 0, it means that x minus a is a factor. Okay, that's better rephrased that way. So those are the main things you need to know by heart as we go into the examples now. So the first example before says determine the nature of the roots of the equation. So we have an equation here, 4x squared minus 7x plus 3. We want to determine the nature of the root of this equation. So you just need to compare. So basically you're looking for the discriminant, right? The discriminant b squared minus 4ac. So you want to check if this will be equal to 0, if to be greater than 0, or if to less than 0, to tell the nature of the polynomial, right? Okay, so they want us to determine the nature of this root, the root of this polynomial, this one here. So you compare it with this. Clearly a here will be 4, right? B, because of the positive sign p, b must be minus 7, right? And then c must be 3. Okay, so that's what you have here. See? So you just plug in the values. You need d equals to b squared minus 4ac. You know what b is. B is minus 7. So you see minus 7. So we're plugging in here. B is minus 7 all squared. You know what a is. A is 4. You know what c is. C is 3. So that's how we got this value here. You just substitute in back. And you know minus 7 all squared, that's 49. And multiplying all of this, you get this. So this is equal to 1. Clearly the value is not, d is not equal to 0 here, but it's greater than 0. Look at it here. It's 1. So it's greater than 0. So because it's greater than 0, what did we say about it? It means that it has two distinct roots. Remember? Let's go back and see what that statement says here. Right here. You see that? It's greater than 0. Since it was greater than 0, we could say that's two distinct roots. So that's the nature of the roots there. Okay? Okay. Next example is also about finding the nature, but guess what? Now there are no numbers. They're basically letters everywhere. This can be scary for students. No numbers, but letters. So you just simply compare the equation again. Compare the two of them. Okay. A here, there's no letter, no number beside it, but just x squared. If there's no number, the number is 1. Okay, so that's why A is 1. B is here. Our B is minus P. You can see that. And our C is going to be minus Q squared. So that's how we got minus Q squared here. So again, you just substitute, plug in the values. So if you plug in, you will get this value you see here. Okay, and if you simplify, you will get this. So you now have to study the nature of the two of the terms. You have P squared, Q squared. Either it is greater than or equal to 0, right? So clearly this statement is going to be greater than or equal, because it could be 0, right? It could be 0. So if it's greater than or equal to 0, what does that tell us? It also has two distinct real roots again, right? So that solves the nature of that polynomial, the roots of the polynomial. Okay. This one says we should find the value of k for this polynomial, and that it has equal roots. Wow, if it has equal roots, basically the discriminant must be equal to 0, right? Because that's what it says, if it has equal roots. So all we need to do is study this. We want to find k. That should be easy. We know d is going to be b squared minus 4ac, right? And we want it to be equal to 0, right? Sorry, because it says it has equal roots, so it has to be equal to 0. So we need to find b squared, we need to find b, we need to find a, we have to find c. And studying this, you can see that a is 2, b is minus k, look at it here, and c is going to be 8. So that's how we got that. So you just plug them in into our discriminant formula for our discriminant, and we know it has to be equal to 0 because it says they're equal roots, right? So simplifying, and you will get this value, and that's the value of k. You can study and pause the video and go through the solution by yourself. Now the next example has to do with the alpha beta one. If you remember the alpha beta, let's go back a little and see what we had then. Right here. If you remember, I said I needed us to remember all of these expansions and note that it's another way of writing this quadratic equation is saying it is x squared minus the sum of the roots times x, that's the product equals to 0, and the sum is minus b over a, product is c over a. I needed you to know this particular ones here too by heart. Let's go forward. You could also solve it anyway, but it's best to know it too. Okay, so we're trying to solve this particular problem. So it says if alpha and beta are the roots of the quadratic equation, this quadratic equation, calculate the value of alpha squared plus beta squared, alpha over beta plus beta over alpha, and alpha cube plus beta cube. So all you need to do is compare this given quadratic equation with the standard form you know it to be, right? So now you know, if you compare that you get these values for a, b, and c. Okay, but now we know from our formula that alpha plus beta is going to be minus b over a, right? And that alpha beta is c over a. You know what a, b, and c are, so you plug them in. So that's how we got those values here. Plug them in. Okay, having plugged them in, our target is to solve for alpha squared plus beta squared and all of this. So we succeeded in getting alpha plus beta, we succeeded in getting alpha beta, but we need this. So how do we get this? Now recall what I told you. I told you I needed you to know this product by heart. So since we're looking for alpha squared plus beta squared, look at it here. It's the expansion of this term here. If you expand this, you should get this this term here. So this is same as this. So all you need to do is just plug in your alpha plus beta, which is 7 over 2 minus 7 over 2. Sorry, 7 over 2. And plug in alpha beta, which is 2, and you would have solved for this. Let's see it. So we found that alpha plus beta is 7 over 2. We found that alpha beta is 2. So you plug in this expansion like I told us we needed to know. So what is alpha plus beta? is 7 over 2, see it here, all squared because there's a square up in the bracket here, minus alpha beta. Alpha beta is 2, that's how you got here. Simplifying, you get this value here. The next thing we needed to find was this. So alpha over beta plus beta over alpha. Simply find the LCM of this. What's going to be the LCM? Definitely going to be alpha beta, right? Just multiply the two denominators. So beta, we're going to alpha beta how many times? It will go beta times. So we have beta times alpha, right? Plus alpha, we're going to alpha beta how many times? Alpha, we're going to this how many times? It will go beta times. So beta times beta, right? Which is beta squared because beta times beta. Okay? So that's how I got this value here. Oh, I think I made a mistake. Let's take it again. Let's do the sum slowly and make sure there's no mistake. So we have alpha over beta plus beta over alpha. LCM will just be alpha times beta, which is alpha beta, right? Or beta times alpha. Beta will go into alpha beta how many times? It will cross the betas out, so you're left with alpha times alpha. Is in the middle here. Plus alpha will cross out the alpha, so because it will go how many times, right? So you're left with beta times beta. So that's how we got alpha squared and beta squared, which is what you see here. Okay. But we solved alpha plus beta all squared before. See it here. Right? And we know what alpha beta here is. It is 2. So that's how we got this fraction here. And you simplify, you should get this final value. Okay? Okay, let's move forward now. The next example says, write the equation of the quadratic function whose roots are alpha squared beta squared, where the roots of the quadratic, and they are roots of the quadratic equation of this. What to do? First thing first, compare this again as we did before with the standard quadratic equation, right? You then find a, b, and c, which is what you can see here, and then you find alpha beta and find alpha plus beta and then alpha times beta. Same procedure. So you find them. After finding them, you remember the standard way of writing them in terms of alpha beta, which is this equation here, right? The same as writing it this way. Once you're told to find the equation for this, just use this, okay? So now we know it's going to be the sum, but we're looking for alpha squared plus beta squared. So it means the sum of our root will be alpha squared plus beta squared, and the product will be alpha squared times beta squared, right? Okay? So it means that we will need to find alpha squared plus beta squared, which is the sum of our roots, and the product, right? But we know this formula, right? Which is what I told us to remember. We know what alpha plus beta is. We got it from our equation given here. We got it from this equation. See, we solved it here. Right here. Solved it here. Okay? So that's what we pulled forward. All of them here right now. Okay, so the sum of the roots is alpha plus beta, right? We know the formula for it. It's this formula right here. So you just plug in and simplify and you get this value. For the products indices, so you have alpha squared, beta squared, right? This is the same as alpha, beta, all squared. But we know what alpha, beta is. It is 2. So that's how we arrived at 4. So what is the formula for the roots again? For the new equation that we're looking for in terms of alpha squared, beta squared, it is this. You understand? So you just plug in the sum, which you have solved as 3 over 2. Plug in the product, which is 4. So the sum is minus 34. Sorry, because there's a minus here. It's 33 over 4, which is this, and the product of the root, which is 4. And that's how we got this here. So if you if you multiply through the entire, if you multiply through this entire equation by 4, multiply by 4, you get 4 here. This 4 will go. That's why there's no 4 at the denominator, and 4 times 4 is 16. So that's how we arrived at this final equation, which is what we seek. Okay. So you can go back through the rewind and forward fast and see how we arrived at this solutions, as you can see there. So first thing first, once you're given any given quadratic equation with alpha beta, first you relate it with the standard quadratic equation, pull out the alpha and the beta, find the sum alpha b plus beta and the product alpha beta. But because you're looking for new roots in the form alpha squared beta squared, you need to remember the standard equation from the standard way of writing it as an equation in x squared minus the sum of the roots times x plus the product of the root equal to 0. So you will now find the sum of the root in terms of alpha squared beta squared. It could be alpha cube beta cube, so you just get alpha cube beta cube plus beta cube and then the product. Then you solve for each one like we had done. Taking us forward, backwards, I meant to say. So you solve like we had done earlier. Solve for each of them the sum of the root, which is this, using the formula that I told us to remember, or the product I told us to remember, and then substitute back into the standard equation that we had written, simplify, and you get the equation you're looking for. Okay. The next example says find the range of the values of k for which the equation x squared minus 2x minus k is equal to 0 has real roots. So we want to find the range for it, and we're saying it has real roots. Real roots meaning that the discriminant is greater than 0, right? So first thing first, again, you always compare with the standard equation, or better still the quadratic equation. You know, when you're given any form of quadratic equation that doesn't look like its standard form, so that you can find a, b, and c, as you can see here. You just compare the two and you get your a, b, and c. I'm sure you've seen and verified that it is so. Now we're told that they have real roots. That's why the discriminant we're using is b raised to power 2 minus 4ac greater than 0. So you plug in the values of a, b, and c, and you have this. Okay. Now, if you simplify, you arrive at what we have here. Dividing through by 4, you get k is greater than 0. Note, the inequality sign did not change because it is only when you divide or multiply by negative sign that the inequality sign changes. So it didn't change, okay? So we found the range of the value for k, as you can see it here, okay? The next question says, find the range of the values for which which are satisfied by the inequality x squared minus 8x plus 15, which is less than 0. We want to find the range of the value that this inequality satisfies. Okay, first thing first, you factorize, right? You can see, factorize it. So if you factorize, I'm sure you remember how to factorize from GSS 3 or using GSS 2. So you factorize, you should arrive at this term here for them. These two values. I'm not going to teach you how to factorize. So factorize, check. If you don't remember, bring out your textbooks from secondary school and factorize. You should get those values. Okay, so it means that either x minus 3 is going to be less than 0, or x minus, one of them just has to be so, meaning that x minus 3 be negative, while x minus 5 will be positive, or x minus 3 could be positive while x minus 5 is negative, so less than or greater than. So that's what we're saying here, that x minus 3 could be greater than 0 and x minus 5 will be less than 0, because that's our intention based on the inequality, right? Okay, so how does that help us? Because we're trying to find the range, right? So if it turns out that x minus 3 is greater than 0 and x minus 5 is the one less than 0, what's the implication of this? If we make x subject of the formula in this inequality, you get that x will be greater than 0 while x will be less than 5. So if you write that as an inequality, x is greater than 3, meaning that we can put 3 at the end and put x in between, and x is less than 5. So this makes sense, right? The inequality shows, which is good. But what if it is the opposite now? You remember I said it could either be that x minus 3 is bigger or it is 1 lesser. So what if it is that x minus 3 is 1 lesser and x minus 5 is greater? If that happens, simplifying, making x subject to formula in the two inequalities, you have this here. For this one, you get this. Oh, how can it be that x will be larger than 5? See, and yet it will be less than 3. Is it possible? Here, watch. It says here that x is greater than 5, and yet it is smaller than 3. That's impossible. So it's not possible to have that. So it's not possible that this range will exist. This range we're trying to evaluate here, the next one here. So the only range will be that x lies between 3 and 5, which is the first one. So that is the range we are looking for, which is our answer. Okay. The next example says find the remainder. So now we're down to the remainder theorem and remember the remainder theorem that we talked about and the factor theorem. So now we're told to find the remainder. And the remainder theorem states that if px is a polynomial in x, then the remainder when px is divided by x minus b is pb. So you need to be able to state this. So we're told to find this remainder when this polynomial is divided by x plus 3. So note, we have a polynomial, right, which is px, and we are given the polynomial. This is our polynomial, and so our px is this polynomial, which is this here, right? So what I've written down here. Okay, we found our polynomial px. It is this. So that's what we've written here. And the polynomial says that the remainder theorem states that if you divide it by x minus b, then pb will be the remainder, right? Our own is x plus 3. Okay, the yellow pen seems brighter. Let's use the yellow pen. So ours is x plus 3. The remainder theorem says it is x minus b, right? So how do we get our values? You just simply equate it to, okay? You just equate them. So let's equate and find out what our x will be. So we have x minus b equals to x plus 3. Clearly the x is cancelled out, so you have minus b is equal to 3, meaning that b will be equal to minus 3. So we found b. Our b is minus 3. So that's how we got it here. See? It's minus 3. Okay. So if b is minus 3, we just simply plug in, because we're looking for pb, which is our remainder, right? So we need to find pb. That is, we're looking for p minus 3. So wherever there is x, we're going to put minus 3 in this equation to find our remainder. Okay, so let's see. Okay, so let's see now. So p3, this is our equation, right? Wherever there is x, it now becomes minus 3. So the x here it will be minus 3 to the power 3. Look at it here. There's a 5 outside, x to the power 2. So the x is minus 3 to the power 2. Minus 2, look at minus 2, and then there's minus x, sorry, x, which is minus 3, and then there's minus 1 at the bottom, last part, which is there too. So you just simply substitute, simplify, and get your answer. And by the time you simplify, your final answer is minus 3. So the remainder, sorry, 23. So the remainder is 23. Okay, so that's how you find the remainder using the remainder theorem. The next example says find the value of m if x minus 2 is a factor of this polynomial. So we're using the factor theorem, right? So what does the factor theorem say? It says if px vanishes when x is equals to a, then x minus a is the factor of px. So that is to say, whenever you plug in the value of a in this x minus a into the polynomial px, and it goes to 0, then this will be a factor. X minus a will be a factor. So we're told to find m, and we're told that x minus 2 is a factor of our polynomial. So if it's a factor, it means that whenever you plug in, so when we had x minus a, we plugged in a and the polynomial went to 0, right? Now we have x minus 2. It means that if we plug in 2, our polynomial p x, which is all of this, will be equal to 0, right? So all we need to do is write the entire polynomial. Wherever we see x, we put in what? The value 2, and see if it will simplify. So now we know that the polynomial PA will go to 0. So this is our polynomial. In our case, A, we plugged in A, but we're supposed to put P2, right? Our A now is 2. Okay, so wherever you see A, you put in 2. So 2 is already in it. Note, M kept following because only the X values that we changed, we put 2. Wherever there's X, we put 2. So you put in 2 wherever there's X. And if you do that and simplify, your final answer must give you that M is equal to -1. And we're through with the solution, which is our value of M we're looking for. Okay, so you can go through the notes, follow it slowly, and if you have questions, ask. Thank you.